Welcome to Sundar's lecture. This is lecture number 23, and in this lecture we are going to start a new topic, propagation delay in logic gates, right? So what are all the topics we have seen in the previous class? See, we have started with the demultiplexers and how demultiplexers are working, and then we have seen what is inside the demultiplexer, the logic diagram of the demultiplexer, and then we have seen how to implement a 1 cross 4 demultiplexer using 1 cross 2 demultiplexers, and then we have seen how to implement a 1 cross 8 demultiplexer using 1 cross 4 and then 1 cross 2 demultiplexer, and we have also implemented full ladder using 1 cross 8 demultiplexer as well as 1 cross 4 demultiplexer. This is for 1 cross 4 demultiplexer, and then we have seen what is encoders, uh, and then we have seen how to convert a decimal to BCD using an encoder, and then we have seen what is parity encoder, because there is a problem in the normal encoder, that is why we have gone for priority encoders. And what is priority encoders? It will prioritize the input. If the second input is present, it won't consider that particular input for the third or fourth inputs, right? So that is what we have seen, and we have drawn the logic diagram. And in this class, we are going to see propagation delay in logic circuits. Actually, what is propagation delay in the logic circuits? For example, you consider this a NOT gate. This is actually a NOT gate, right? So we will have V input and then V output. And what is the process of the NOT gate? If 0 comes, it will generate it to 1, and if 1 comes, it will produce the output as 0, right? So for example, we consider this is input now, this is the input voltage, and this is now low here, and it becomes high at this point, and then it is holds on to high until this point, and then it is going to become low at this point, and then it is going to be hold at low here. So this is the waveform of a input signal now. And what happens to the output signal? See here, this particular point, see, we cannot increase an input signal from 0 to high at a single instant. For example, it never gets to high like this. Actually, we are expecting like this, right? Can you understand? This has to be like this, and this output has to become low because this is an inverter, right? So it becomes if V in becomes 1, then V out has to become 0, and then this has to come like this, right? This has to be like this, and this will not happen exactly like a square wave like this. So what happens here? This input will gradually increase, and then it becomes high here at this point, and after this point only the output is going to 0, and it will not also goes to 0 at a single instant. It takes time to go to 0 at this point. Then what happens here? This is the midpoint. So we generally have the output input high and then output low at certain points. For example, this whole part can be considered at the midpoint. This midpoint is now being selected as the high, and this midpoint is being selected as now low. So I am just taking from this point to this point, I am just considering, that's all. So until this point to this point, I am just considering it to be TPHL. And what is this TPHL? HL, this is propagation delay from high to low, from high to low, right? This is now happening here, and then here you see from this point to this point, again there is a delay in becoming this output is not 1 at this instant. Actually it has to be 1 at this instant, but it is going to happen at this point. So this period we generally call it as TPHL, propagation delay from low to high. So what happens here? The logic operation realized by the logic gates have finite propagation delay. And what is the finite propagation delay? This is the propagation delay, TPHL, and TP LH. So while it is going from 0 to 1 or it is coming from 1 to 0, there is a definite delay. So the output of this NOT gate will take certain time to produce the next output if the input is changing, right? That is the whole idea. This is called as propagation delay. And in general, the propagation delay for TTL is approximately equal to 10 nanoseconds, and for CMOS it is approximately equal to 50 nanoseconds, and it also depends on the load, also supply voltages for CMOS. For example, I have not we have not covered TTL and CMOS, and we will cover that later. But for now, you try to understand, you can implement the logic gates using TTL as well as the CMOS, right? So these two are the propagation delay. And what this propagation delay is going to do in the logic gates, and which causing us the glitches in the logic circuits. For example, what is glitches now, right? Glitches and hazards in the logic circuits. What is this one? Glitches are undesired positive or negative going pulses in a digital logic circuit, and glitches occurs due to finite propagation delay of logic gates and occurs for specific combination of inputs. Glitches is transient in nature and has short duration. That means it is nearly nanoseconds, right? And a logic circuit has hazard if there is a potential for glitch. For example, see, this is the desired output of particular any gate, right? What is this one? Actually, this is 0. This has to be the output, desired output of a particular circuit. But what happens here, due to this propagation delay, if there is a change in input, this 0 will go to 1 momentarily. Actually, this is 1. This is 1. It goes to 1 momentarily, and then it comes to 0 again. Then it will stand in 0. And also for this is also desirable. For example, if the desired output of the logic circuit is 1, this will holds on to 1 for a moment. It will goes to 0 here, and then it will come to this period, this particular thing. It is happening because of changing input, right? So it comes to 1 again. So what happens here, the desired output is 1 here, but it is going to 0 for a particular moment, and the desired output is 0 and it is going to 1 for a particular moment. So this is called glitches, the unwanted positive and negative pulses in the logic circuit, right? So we have to uh, eliminate these kind of glitches in the output of a logic circuits. If we don't eliminate these kind of glitches, then the desired output will not be pursued in the output of the logic circuit. So that is what we are going to see here. We will take an example of how a glitch occurs in the logic circuit. For example, we consider this is to be a logic circuit. So what is happening here? What is this one? This is an AND gate. So what is the output we will get here? This will be A dot B, right? So this is the output of this one, and here this input will be here A bar. This is because this is A, so the NOT gate will make this A to A bar, and this is C, right? So what you will get here, this is A bar C, and what is the output of this one now? So Y will be is equal to A dot B plus A bar C. So this is the output of this particular logic circuit, right? So what happens here, when does a glitch happens here? So for example, you take this one, let we assume B to be 0 constantly and C to be also 0, and we are not going to change these two input now. Now what we will do, we try to change this A from 0 to 1, from 0 to 1. That is what we are going to see in this particular logic circuit, right? First what we will do, we will consider another case. This is also one case, but we will consider another case. See what we are going to do now, we will take this input B to be 1 and C also to be 1, and what we are going to do now, we are going to make this A is equal to 1 to 0, right? What will happen now? So see here, this is 0. So we will take this to be 0, sorry, this to be 1 and this to be 1 and this C to be 1 now. See, this is now we are having as an input. So what will be the output of this particular circuit? So if this is 1, so this is 1 and then this is also 1 and this is 0 and this is 1. So 1.1 will give you 1 plus this will be 0 and y will be is equal to 1. That is the output, right? So if A is changing from 1 to 0, if A is changing from 1 to 0, what will happen? This will become now 0, right? So if this is going to become 0 and even though you just substitute in this equation, this is AB plus A bar C, right? So what will happen now? So this is now 0 and this is now 1 and this is now 1 because A bar, right? So this is 1 and C will have, it has to be 1. So this is 0 plus 1. So what is the output now? This has to become 1. So what is the idea of this circuit? Even if you change this A from 1 to 0, the desired output of the logic circuit has to be 1 in both cases, right? 1 1 1, the output should be 1, and even if you change this 1 to 0, the output should be 1. What will happen here? That is the idea. If I change this 0 to this 1 to 0, then what happens? This gate in this particular input is instantly goes to 0, right? But what happens here? If I give 0 to this particular input, this will be changing from 0 to 1. But the problem is this NOT gate will take an extra time because of the propagation delay. If it takes an extra time of a propagation delay, what happens now? This is already 1 and then this, maybe I will write it in the red color, this is already 0, right? So if this is 0, this would have been 0. And if the one input of AND gate is 0, this will be also 0. And what is the output of an OR gate now? This is going to 0. Try to understand. This is now 0 for the propagation delay. Until the propagation delay. This NOT gate has to make this 0 to 1, but it will take that particular time. What is happening around here? If this is 1, the output is 1 here until this point, and if I make the A to 0, then what happens here? This NOT gate is taking the particular time to make this output to 1, so it is already 0. So at this particular point, this output is going to 0. Try to understand. Try to understand, right? This is actually going to 0, and if this 0 has become 1 here, then what happens? This becomes 1. So this is already 1. So this output will be 1 because AND gate will make output to 1 if both inputs are 1. So OR gate will make this output to 1 if any one input is 1. So again, what happens after that propagation delay? This is going to become 1. See, what is this one? What is this one? Huh? This is called as glitch. Glitch, right? Why it is happening? Because of the propagation delay of this particular NOT gate, and this glitch has to be eliminated from the logic circuit output, right? That is our ultimate aim we are going to do now, right? One more thing, how can we find a particular output expression has glitches or any kind of hazard it is going to produce in the output, right? So for example, we are having expression like AB plus A bar C, right? Now what I am going to do, I am going to make this B to be 1 and this C to be 1. Then tell me what is the output equation it will be now, because this is now 1. A multiplication of 1 will give you A, and then plus A bar multiplication of the C is 1, so it will give you A bar, right? And then you see this one, what is this actually? This is tautology, right? Tautology. What is tautology? What is tautology? The result always be 1. And if you see any tautology condition in any particular output expression, then that output expression obviously going to make the glitch. And what is that particular glitch? It is static 1 hazard. It is static 1 hazard. And that is what we are going to see now. What is this one now? We are going to see static 1 hazard, right? So, what is the output of this particular expression or this gate? Y should be is equal to what? This is an OR gate, so it has to plus now. So, what should be this one? So, A and this is A, this is A bar, so A plus A bar. What should be this one? What is this one? Tautology. So, if it is tautology, then output should be 1 always. That is our particular idea. But what will happen now? If this A is going from 1 to 0. For example, if this is 1, if this is 1, then this one will be 0. So this one makes the output to be 1. We know this one. But what happens now if this one tend to 0? Right? What happens now if this one tend to 0? This is going to become 0. So straight away this one is 0. But what happens here? What happens here? This particular NOT gate has propagation delay. So this 0 will not be going to become 1 instantly, and it takes its own time to make this 0 to 1. So this one will be 0, and if this both inputs are 0 to OR gate, then obviously this output is 0 now. And what happens now? That is what I have just written here. This tau 1 is the delay created by the NOT gate, this particular NOT gate, right? Now what happens after the delay? This 0 going to become 1, and now this is 0 and then 1. What happens here now? This OR gate will take again a propagation delay will be there to process this input to output. So what happens now? This OR gate will have a finite propagation delay here. See here, this T2 is the propagation delay of the OR gate. Now what happens? So until this point, the output of Y, this point, until this point, here and then here, the output goes to 0, and then only it will comes to 1. Try to understand. So this is called static 1 hazard. What is static 1 hazard? The desired output is 1. The desired output is 1, but it goes to 0. But it goes to 0 for a moment, and then it comes to 1. So this is called as static 1 hazard, right? This is 0 and this is 1. This is called as static 1 hazard, right? Now how to detect the static 1 hazard? See, it is very simple to detect the static 1 hazard by using the Karnaugh map, right? While deriving the expression from the Karnaugh map itself, we can find the static 1 hazard. So now what is the output expression of this one? So I will just write it down. Y will be is equal to, this is actually B bar C, right? So it is B bar C plus, since it is SOP, then this one will be A, and then what is the common term in these two? It is B. So this is the output expression, and you can see here it is B bar, it is B. So if you make A to be 1 and then C to be 1, then what happens to this expression? It will become now B plus B bar, B plus B bar. So what is this one? So obviously you can see that it is tautology. So obviously it is going to be a static 1 hazard. So when this is going to happen, very simple, you have B plus B bar, right? So you have A and then B and then C. So you are having A is equal to 1 and then C is equal to 1. So there is no problem. So from 1, 1, 1, 2, 1, 0, 1. This 2 will not change. These two inputs is not going to change. But this B is going to change from 1 to 0. And if it is so, you just draw the diagram like what I have drawn here in this example of glitch. You can easily get this idea to this particular example, and you can just find out the glitch will happen, and that glitch is here. It is static 1 hazard, right? So what is static 1 hazard? The expected output should be 1. For a moment it will go to 0, and then it will come to 1 again, and it will withstand, and that particular moment is it is because of the propagation delay, right? Now this is the problem. When the input changes from 111 to 101, then obviously there is a static 1 hazard will happen in this particular output expression. And how we can eliminate this one, that we will see separately anyhow, that we will see separately, but there is a glitch. So obviously this is a static 1 hazard. And how can you find from here? Can you write the expression y should be is equal to what? This one is b bar c. This is b bar c plus you can see this is b c bar, b c bar, and you can see that even if you put anyone cannot make into constant. And see one thing, I will tell you here itself. You see these two are essential pairs, right? These two are essential pairs, but this two ones can be also made into another pair, but we have not done that to minimize the expression. And if it is so, then hazard will happen, hazard will come. This is not covered by us, but you see in this example, is there any possibility to cover one in this grouping and in this grouping by combining any ones in these two groupings? No, there is no any one that can be covered by an extra pair in these two groups. So what happens here? This here no hazard will be happened, but here hazard will be happened. And if you put c is equal to 1, what happens now? This will be 0. And if you put b is equal to 1, what happens now? B is equal to 1, then this expression will be 0. So there is no tautology possibility is here. So there is no hazard 1. Static 1 hazard will not be there in this particular expression. That is the whole idea. And you can see here, this is the another example. And what is the expression of y here? So y can be written as the, what is the common term in these two? I have to write the common term in these two. It is b. It is b. And then the common term in these two, it is c, bc plus. And what is this one now? This is actually c bar, d bar, c bar, d bar. And what is the common term in these two? It is a. So what happens here? You can easily find the tautology condition. How? So a you take it to be 1, and then b you take it to be 1, d you take it to be 1. And what is the expression? You will get it down. So y should be is equal to b and then c. So it will be c plus, and this c bar you just keep it down. So d bar, oh sorry, this one you take it to be 0, right? So this is 1 now, this is 1, so this will be the condition, right? So what is this condition? So this is obviously tautology. So if there is a tautology condition, then what I have told you, there will be static 1 hazard. Obviously there is a possibility for static 1 hazard. So how it is possible? From for example, when this static 1 hazard will happen, so this is a, b, c, d. So when your input is 1, b is 1 and c is 1, also d is 0 now, this input is changing from 1 1 1 0 to 1 B is 1 and this C is going to become 0 and this D is already 0. So when this change is happening from 1110 to 1100, this particular expression logic circuit will have a static 1 hazard. This is the idea. Try to understand when it is going to happen. That also you can easily find from the particular expression. So I have concluded that I have a static 1 hazard here. So how can I eliminate? So you can also see that this is one group and this is another group. Is there any possibility we have not covered? It is not an essential grouping also. So what is that one? Actually we have not covered this one and this one with a pair. Right? These two groupings can be combined with another pair that was not covered by us because to minimize the expression. And if it is so, then obviously you will have the static 1 hazard, obviously. And in this expression also, if you cover these two, we have not covered these two, so there is a static 1 hazard. Here there is no possibility, so there is no static 1 hazard. Simply you can conclude by this way, right? So the next one will be covering static 1 hazard for this particular circuit. Right, I have just drawn the diagram for this equation. See here, I have just drawn this one, and we have already discussed this will have a static 1 hazard. So how can we eliminate the static 1 hazard? Make this pair into account, and if you do so, what will happen now? This y expression y will be now, this is already there. So this is B C bar, B bar C, and then AB will be already there. Put plus, you have another expression now. This is A, and what is the common term in these two? It is C. So put this one, and you can eliminate the static 1 hazard. See, when static 1 hazard happened in this particular expression, when you make 1 1 1 2 1 0 1, that is what we have seen here. Try to understand. See here, we have seen here. So we will check it out for this one, how to eliminate, and I am just going to draw the diagram, and you see I have just drawn this diagram for this expression, and you see now when this is going to happen. So if A is equal to 1 and then B is equal to 1 and then C is equal to 1, so what is the output now? This AB will be 1 and this B bar C will be 0, but this is AC actually, right? So this is AC. So this is also 1. So this A is 1, then C is 1. So what happens now? This output will be 1. And what happens here? If this B is going to 0 now, if this is going to 0, then what happens? This is going to 0. So this is already, here it is 0, but this 0 will be here. So it takes an extra time to make this one to 1 now. So that the problem has happened here. But what happens now, since this A and then C, it is not going to change, right? It is not going to change. So this will make by default, even if B is changing from 1 to 0, this gate will make this to 1. So obviously this output will be always 1. Even if this B is going from 1 to 0, so that this 0 is going to make this particular input to be 1. After some time, this particular gate making the output to 1. I am not going to consider this one. This propagation delay of this gate and this gate will not going to affect the output as 1 to 0, because this gate is making that particular 1 to become it will make the output to 1. So this is how you can eliminate the static 1 hazard. So what we have done, we have just taken an extra grouping that was not covered in the Karnaugh map. Simply, it will eliminate, right? Right. What we will do now? See here. What is the output expression of this one? y will be is equal to, I have just written already, right? I have just written already here. What is this expression? BC. So I will just copy this one so that it will be very easy, and I can put it down here. So we have already seen, right? This particular circuit is making static one hazard. So how can we eliminate this one? By making this into pair. So that is what I have done here. This pair has to be taken into account. So the output expression now has to become from, this is from here, and I am just writing from here. So uh, y will be now is equal to this BC is already there, and then this A C bar, D bar is already there, and put extra one pair, that is this one. So it is actually AB, straight away it is AB. And what is the common term in these two? It is D bar, right? It is D bar, right? So D bar is the common term. And this will eliminate the static one hazard as we seen here. Whatever we have seen here, you just apply this one to this particular output expression. Draw the diagram and verify the static one hazard will be eliminated. So I am not going to draw and explain it again, because I have just given you a brief idea about how to eliminate. Very, very simple. You don't need to panic here. Just make an extra pair covering these two groupings. Try to understand. Try to understand. You should not make these two ones to be an extra pair so that the hazard one is eliminated. You cannot say like that. Try to understand. You have to group two different groupings with one extra grouping. Then only it will eliminate the static one hazard. Try to understand. These two ones should not be covered again, because this is only in one grouping. So this is how you can eliminate the static one hazard. So what are all the topics we have seen in this class? See, we have started with the propagation delay, and I have explained you what is the propagation delay. And then we have seen glitches and hazards in the logic circuit. What is glitches? Undesirable positive or negative pulses in the output of the logic circuit is called as glitches. And we have seen two different hazards. One before that we have seen what is glitches and how it is happening with an example circuit. And then we have seen static one hazard and how it is happening because of the propagation delay of the logic gates. And we have also seen taken a example how to detect the static one hazard, and we have taken 2-3 examples, and we have also covered how to cover the static one hazard, and we have eliminated here by by putting extra one group in the Karnaugh simplification, and we have seen an extra example. See, we will see what is static zero hazard in the next class. Thank you.